Hello everyone, I am D. Narendra Verma. I am going to give you a small lecture on shaft couplings, which was from your course Design of Machine Numbers 1. And in this, the main contents are rigid couplings. In this, we are going to study the design about muff couplings, split muff coupling, and flange couplings. And the next topic is flexible couplings. In this, we are having a bushed pin type flange coupling, which is the modified one of flexible coupling. In this lecture, I am going to tell you about the design of muff coupling. Firstly, what is a coupling? A coupling can be defined as a mechanical device that permanently joins two rotating shafts to each other. This is the basic definition, which means we are having two shafts. There is an input shaft and an output shaft. The power will be transferred from the input shaft to output shaft, okay, with the help of a coupling. The main examples are output shaft of an engine to input shaft of a hydraulic pump. For the working of a pump, we need to give the power. That power was given from an engine. The output shaft of an engine is connected to the input shaft that will run the pump, okay. Similarly, an electric motor to gearbox of machine tool. Generally, if you take a lathe machine, for running the spindle, we need power. The power will be generated by the electric motor. From the output shaft of the electric motor is connected to the input shaft of the gearbox, which will give the power to run the machine tool, okay. Similarly, electric motor to a compressor. These are the examples for couplings, usage of couplings or applications of couplings. Next, these are some types of couplings. Generally, if you take the shafts, here there are two shafts. The one will be the input shaft and the other will be the output shaft. Here a crank is connected to the input shaft, and here the flywheel is connected to the output shaft. If the two shafts, the axis of the two shafts are parallel, we can use Oldham coupling, okay. If there is a small offset, this offset can be compensated by this intermediate disc, okay. And this is a Hooke's coupling or universal coupling. And if there is any angular misalignment, or this is when the axis of the shafts meet at a point. This is the axis of the driving shaft and this is the axis of the driven shaft. These two shafts will meet, the axis will meet at a point, okay. In this application, we can use universal coupling. These are some of the couplings, and the main couplings are basically we classify the couplings into rigid couplings and flexible couplings, okay. The rigid couplings are the simple ones and the flexible couplings are the modified ones, okay. The rigid couplings cannot tolerate misalignment between the axes. If there is any misalignment between the output shaft and the input shaft, those cannot be tolerated by rigid couplings. The exact alignment of the shafts should be there in rigid couplings. In flexible couplings, it can tolerate up to 0.5% angular misalignment and 5 mm axial misalignment with the help of some other parts like bushes or discs, which are going to run in the upcoming topics. And the rigid couplings are used where motion is free from shocks and vibrations. If there are any shocks and vibrations in the couplings, then we cannot use these rigid couplings, okay. The purpose, if we are using this coupling in a machine element, if there are shocks and vibrations in that machine element, we cannot use these rigid couplings. Okay, but the shocks and vibrations can be absorbed by the flexible couplings, so we can use the flexible couplings in those applications. Next, the design will be simple in rigid couplings, so because there are less number of parts, and the cost will be less compared to the flexible couplings. And these are having some additional parts like bushes and discs in flexible couplings, so these are costlier compared to the rigid couplings. Next, requirements of a good coupling. The basic purpose of a coupling is to transmit torque from the input shaft to the output shaft. This should be done by the good coupling. Next, a good coupling should keep two shafts in alignment. The shafts should be aligned while they are working. If there is any misalignment or something, that coupling is not working good. Next, easy to assemble and disassemble for repairs and alterations. The good coupling should be easy to assemble and disassemble if there are any repairs or any changes we need to done for them. Next, sharp edges and failure of revolving bolts, heads and other parts should be covered. The proper shielding should be done in order to avoid any failure of, if there is any failure of the revolving bolts, that will come out and hit the operators or any equipment near that failure parts. So the proper guides should be, or covering should be done. For this the cost will be increased, but this should be done for a good coupling, and sharp edges are to be avoided. Next, the main topic for this lecture was the muff coupling. This is a simple type of coupling and it is also known as sleeve or box coupling. This is a basic type of rigid coupling, muff coupling, and it does not have any projected parts, and it is compact in construction. The main parts will be input shaft and output shaft. These are connected with the help of a key and a sleeve. The sleeve will be like a hollow shaft, okay, with a length 3.5D and diameter 2D plus 13. This is cheaper compared to remaining type of couplings. The main disadvantages are difficult to assemble or dismantle, because the length of the sleeve is more compared to remaining type of couplings. The assemble and dismantle will be a little tougher. Requires accurate alignment. The shafts, input shaft and output shaft, the alignment should be in line. The axis of the input shaft and the output shaft should be in line. If there is any misalignment, it cannot be tolerated by the muff coupling. Requires more axial space. The axial space should be more for this coupling. The sleeve length will be 3.5D. This axial space required for this coupling will be more, and cannot tolerate any misalignment, any linear and angular misalignments. This axis should be in line. If there is any misalignment, it cannot be used. Next, the design of a muff coupling. The basic steps are, these are the steps we need to follow while designing a muff coupling. First step will be calculate the diameter of each shaft. The diameter will be calculated by using the equation. This is the torque equation. Power P is equal to 2 by 60. From that we got the T. Torque will be here. The torque is denoted by the subscript T, which is a turning moment or twisting moment. Here into 10 power 6 was given because if we substitute the power in watts, then the torque will be in Newton meter, but we are doing the design in mm, so we are doing, if we substitute here kilowatt, we should do into 10 power 6, and if you substitute watts, you can multiply into 10 cube for converting the meters to mm. Okay, this is torque T is equal to 60p by 2 pi n, and from the torque equation we can find out tau is equal to 16t by pi d cube, or 16 mt by pi d cube. By using this equation we can find out d, the diameter of the shaft, small d. And the second step is calculate the dimensions of the sleeve by the following empirical relations. The diameter of the sleeve, which is a hollow shaft, or outside diameter, will be 2d plus 13. This we have to find out. And length of the sleeve 3.5d. This we have to find out. And then we have to check for the stresses in the sleeve by using the equation tau is equal to tr by j, or tau is equal to mtr by j. Okay. Now j will be, we are considering the sleeve as a hollow shaft, that j will be pi into capital D power 4 minus small d power 4 by 32, and r will be capital D by 2. The next step is determine the standard cross section of the flat sunk key from the table 9.3. This is, there will be the cross section values for flat sunk key, the design values. From that we have to find out, we have to select the dimensions of the key, or we can find out using this. These are the dimensions of square and rectangular sunk key based on the shaft diameter. Based on the diameter we can select the key size, or from the thumb rule we can find out b is equal to d by 4 and h is equal to d by 6, or we can find out by using this empirical relations, d by 4 and d by 6. And the length will be L by 2, capital L by 2, where capital L is the length of the sleeve. And after finding out all these dimensions, we can check for the stresses in the key. For this, tau is equal to 2t by dBl. This is the check for the torsional shear stresses, and sigma c will be compression stresses, check for compression stress, which you have already done in the previous chapter, keys. Okay, generally the sleeve is made of, the shafts and keys are made of plain carbon steels, and the sleeve is made of grey cast iron of grade FG200. Okay, if the stresses are within the limits, the design will be the same here also. This is an example problem we are going to do now. Design a muff coupling to connect two steel shafts transmitting 25 kilowatts power at 360 rpm. The shaft and key are made of plain carbon steel 30C8, SYT and SYC. Yield tensile strength and yield compressive strength of 400 Newton per mm square. The sleeve is made of grey cast iron FG200 of ultimate tensile strength 200 Newton per mm square. The factor of safety for shafts and keys is 4, and for the sleeve the factor of safety is 6 based on the ultimate strength. We are going to design this muff coupling. The given data was, the power is given 25 kilowatt and the speed is given 360 rpm. From this power and speed we can find out the torque. Okay, and for shaft and key, the SYT and SYC is 400 Newton per mm square and factor of safety 4. For sleeve, SUT is equal to 200 Newton per mm square and FO is 6. The first step, we are going to find out the permissible stresses. The permissible stress for shaft and key, because the material was different, plain carbon steel for shafts and keys, and this was grey cast iron FG200. So for the material shaft and key, sigma T, allowable tensile stress, is equal to SYT by FOS, 400 by 4, which will be 100, and sigma c is also same because yield compressive and yield tensile strengths are same. And tau is equal to SSY by FOS, 0.5 SYT by FOS, 0.5 into 404, which is 15 Newton per meter square. And for sleeve material, the ultimate tensile strength was 200. The tau is equal to 0.5 SYT by FOS, which is 0.5 of 200 by 6, which is 16.67 Newton per meter square. And after finding out these permissible stresses, we need to find out the diameter of the shaft by using the relation power P is equal to 2 pi nt by 60 and tau is equal to 16t by pi d cube. This mt is equal to 16 into 10 power 6 into 25 kilowatt. Here we got the torque in Newton mm, and substitute this torque in this torque equation, 16 mt by pi d cube. We get the diameter d, and this is the diameter of the shaft, 40.73. Generally we in the market we can't find the shafts of this size, so we can take 45 mm from the standard tables. Next we need to find out the dimensions of the sleeve and check for the stresses. Dimensions of the sleeve: the diameter of the sleeve, which is the outside diameter of the hollow shaft, 2d plus 13, that will be 103 mm, and length 3.5d. And we can find out the stresses, whether the stresses are within the limit or not. We got the permissible stress of 16.67. We are going to find out the tau for the sleeve, Tr by J. The T will be already calculated, and R will be the D by 2, which will be 105 by 2, 52.5, and J is the polar moment of inertia, pi d power 4 minus capital D power 4 minus small d power 4 by 32. And substituting all these values, MT, R and J, we can find out the permissible shear stress, that is 3.02, which is less than 16.67, so the design will be the safe for the sleeve. Next, the dimensions of the key. We have to find out the dimensions of the key from the table 9.3, or you can find out using the relations B is equal to D by 4 and H is equal to D by 6, or you can see the table. Around 45 mm we get for the shaft, 44 to 50 we have to take the key size as 14 by 9, where 14 is the width and 9 is the height of the key. By taking those values, and the length of the key as L by 2, where the L will be the capital L will be the length of the sleeve. This is the key we are going to select, and after selecting the key we should check for the stresses in the key. So the stresses, check for the stresses in the key. The stresses we got 26.32. These values we have already got. Substituting these values we get 26.32 as shear stress, and which will be less than 50. We have already calculated the permissible shear stress for the key material, shaft and key material, which will be 50. The 26.32 is less than 50, so the design will be safe. And the compressive stresses we have to use 4 MT by DHL. We got 81.87, which is less than 100 Newton per mm square, so the design will be safe. This is how we are going to design a muff coupling, which is very easy, which is simple in design, and you should also draw the muff coupling after the design. Okay. For the reference, you can use V. Bhandari Mission Design Textbook, and for Design Data Handbook, MD Jabaluddin. You can use this textbook for references. Thank you.